Hi everyone, this is the recording for the year 12. Well, not really. Jan Mark. So, let's get started. First question. Predict the ionization equation, including state symbols, to show the reaction that occurs when the first ionization of lithium is measured. Lithium, gaseous state, becomes lithium ion plus an electron. Next question. Predict and explain the general trend in first ionization energies for the period 3 elements, aluminium to argon. Hold on one second, let me pull up the periodic table. I'll just enter it here. Here we go. Alright, so for period 3 elements from aluminium to argon. So ionization energies, they increase. So because increased number of protons, increased electrostatic force of attraction between outer electrons and nucleus more energy to remove outermost electron. I'd just like to add that there is the same shielding, because that definitely gets you one of those marks from there. So let's move on to the next question. It says, there is a similar general trend in first ionization energies for period 4 elements, from gallium to krypton. State how selenium deviates from this general trend and explain your answer. So let's take a look at selenium's position. So period 4 from the selenium. Selenium, here it is. So let's highlight that so we can visually see that. So it's in a P block. This is P1, P2, P3, P4. So selenium has lower IE because its outermost valence electron is in the 3p, is it? 3p? 1, 2p, 3p, 4p, sorry, 4p energy level, but it is paired. More repulsion, easier to remove, less energy required. So I think that answers that question. Let's move on to the next one. Suggest why the first ionization energy of krypton, sorry, I'm just doing something. Okay. Suggest why the first ionization energy of krypton is lower than the first ionization energy of argon. It has one more energy level wait, hold on, krypton and argon, yeah, so more shielding. Less energy required to remove electron. Okay, let's carry on. The table below gives the successive ionization energies of an element. Deduce a group in the periodic table that contains this element. Alright, so we see a clear jump here, 3,000 kilojoules around, even 4,000, and here it's relatively, so it's in the group 2, because it has 2 outermost electrons. Identify the element that has a 5+ ion with an electron configuration of this. So 5+ means it's missing 5 ions, so we're going to add 5 to each of these numbers. So 2 plus 2 plus 6 plus 2 plus 6 plus 10, and we're going to add plus 5, and that gives us, let me just do it on my calculator, is 33. So what element has the electron number of 33? Arsenic. Arsenic. Next. Which of these samples of gas contains the largest number of molecules? PV is nRT. We have R, we have volume, we have pressure, we have temperature, so we're looking at moles. Alright, so moles, N, is PV over RT, just because we take these to the other side. So we're just going to do the calculations for each of these and see what number we get. Times volume. Sorry, I'm just doing this on my calculator. So here we have 0.2 moles. Here, one times 400. This is 0.24. Hold on, let me just add some more decimal places since it seems like we need it. Part C, PV, PV times 10 power 4 times volume. Oh, hold on, we need to change this to meters cubed. So we need to divide by 1,000. So that's actually 3 times -3 times the pressure. So here it's 0.02. And finally, the last one is, well, we need to change this again. 10 power 2 times 10 power -3 is 10 power -1. So this is actually this. So this one is 0.16. So the largest number of molecules, it's going to be B. So I hope that's the right way to go. I'm not really sure about that. Okay. What is the total volume of gas remaining after 20 centimeters cubed of ethane is burned completely in this amount of oxygen? ethane. So we know this is 20 centimeters cubed, which is in fact, we're going to divide it by 1,000. 1, 2, 3, 0, 0 decimeters cubed, which is in fact, hold on, 20 times 10 power negative 2 times 10 power negative 2, which is 2 times 10 power negative 5 meters cubed. And this one is 1 times 10 power negative 4 meters cubed. All volumes are measured at the same pressure and the same temperature. I don't really understand. What is the total volume of gas remaining? Is this a continuation? No. Well, perhaps I just need to add them together. A 1.2 times 10 power negative 4 meters cubed, so we just need to multiply by 10 power 6 is 120 centimeters cubed, so I guess it's this one. Let's carry on. A saturated aqueous solution of magnesium hydroxide contains this much this. Okay, so we know that mass is 1.17 times 10 power 3 grams. And volume is, so here you can see it's decimeters cubed, so let's turn this into decimeters cubed. So divide by 1,000, 1, 2, 3, 0.1 decimeters cubed. MR is mg, which is 24.3 plus 16 times 2, which is 32, plus 2, which is, so that's 58.3. N is M over MR, so let's do that. Okay, 2.007 times 10 power negative 5 moles, and maybe we can divide this by that. I guess it's this one. That's what I got, but I don't know why they mentioned the ions here. Not really sure. Okay. Ethanoic acid is synthesized on an industrial scale by the oxidation of butane in the presence of metal ion catalysts. Balance the equation given below. Okay. So, let's try 4 here. 4. So that's 12 plus 4 is 16H. That doesn't really balance. Let's add, let's say this. Five oxygen. Let's try 6. 6, 3. That makes 12H here. And 4H here. So what multiple of this? 12 plus what gives you, you can do this, and this becomes this, and therefore 6 plus 2 is 8, 8 hydrogens here, I'm not exactly sure about this. Okay, we'll draw a star just because that's 1 mark, and it's quite time consuming. The second method involves the oxidative fermentation of ethanol in the presence of bacteria. The equation representing this reaction is given below. In a small-scale experiment using this second method, it was found that 23 grams of ethanol produced only 5.45 grams over 23. Yield must be percentage. Alright, so 23 grams of ethanol, MR is 2 times 12 plus 5 plus 16 plus 1, which is 24 plus 16 plus 1 plus 5, which is 46. And so 23 divided by 46 is half, I think. Yes, 0.5 mole. And 5 ethanoic acid. So MR of that is 12 plus 3 plus 12 plus 32 plus 1. What is 3 plus 32 plus 1? Is 60. And so 4.54 divided by 60 . 0.06 mole. 0.6 over 0.5 times 100. I'm just curious, percentage yield Chem formula. Units. Oh, we use grams. What about atom economy? Alright, so we did this one wrong. I'd just like to write it down in my notes. Just give me 1 second. That, well, okay. Percentage atom economy. Percentage atom economy is MR over total MR times 100. Percentage yield is grams, so grams over total grams times 100. So essentially what we did is not worth 2 marks. So I'm just going to quickly erase all of this very roughly and just use a different color just to distinguish. So 4.54 over 23 times 100 . %. Let's carry on. Explain why CF4 has a bond angle of 109.5. 4 covalent bonds. Due to electron repulsion, bond angles must be as large as possible. Must form tetrahedral structure with 109.5 degrees bond angle. I'd just like to square off some key points here, in a different color of course. For covalent bond, we mentioned that. Electron repulsion, as large as possible. Okay. Ooh, we have some enthalpies of formation. Okay, that's very, very important. The enthalpy change for the following reaction is this. So it loses energy. Forward reaction loses energy. Use this value and the standard enthalpies of formation in Table 1 to calculate the standard enthalpy of formation of this year. Okay. So let's try and figure it out. So what we have here, F2, so to form this, it's 0 kilojoules, sorry. And let's carry on. We know that CF4, I'd just like to form it, we need 2 times negative 680, and HF, 6HF. To form it, we need 6 times negative 269. So we are actually breaking this, but we're forming this. So breaking this takes in energy plus 0 kilojoules is, this is formation, so it releases energy. So in fact, we're going to keep it as it is. So 2 times negative 680 is negative 1360, and 6 times negative 269 is, 4 here, 4. So is negative 2974, and we know that something minus this is negative 2889. So 74 plus 2889. Hold on. Enthalpy of formation. I'm just going to subtract them, I'm sorry. I know it might be wrong. No, it can't possibly be. 5863 kilojoules per mole, I hope. 5863. I so hope this is right. So this entire side takes in 5863 kilojoules, but releases 2889's worth, and you get 2974. sorry, 2974. It releases this much. Something is wrong. $889 plus 2974 is 85. I'm just going to go with 85. 85. So it takes, to break, it takes in 85, but releases 2 times 680. Sorry about that, yeah? 2 times negative 269. Sorry, 6. I do keep making that mistake. Okay, I'll just go forward with that. Methane reacts violently with fluorine according to the following equation. The mean bond enthalpies are given in Table 2. A student suggested that one reason for the high reactivity of fluorine is the weak FF bond. Okay, so let's try and find out the strength of that FF bond here. So, CH4, we have 4 of those. 1, 2, 4, 1, 2 times 4, 1, 6, 4, 8. 4, 8, 4 times 1 is 4, 8, 4. And 4 times 5, 6, 2. Now bond enthalpy is the energy required to break a bond, I guess, yeah. So to break a bond, it takes this much. So we will leave this one here, but we're going to negative both of these. 1648 minus 484 minus 2248. What we should get is minus 184 this. And if we divide it by 4, it's just 1 kilojoules per mole. I just want to double check that this is right. So to break these, we're actually breaking that plus 2 times negative 271, and to make them, we're going to do the negative of that. So negative 484, sorry, negative 484, yeah, plus minus 2248. Why is this the case? Let's try 4 instead. Oh. Did I forget minus 4 meter? Okay. Maybe I need a positive value for this. I'm not good at this section. Let's do it again. Okay? Bond enthalpy, the energy needed to break a bond. Okay? So, energy needed to break bonds, breaking. We have 4 of these, and one of these, and 4 of these, yes. And this is in fact F, 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 F. So we have 4 of a question mark. Now we're making the following. So we're making 4 of these, and we're making 4 of these. So let me just do it. 1, 6, 48. 1, 9, 3, 6. 2, 2, 4, 8. Okay. Now breaking is the correct sign. So 1, 6, 4, 8 plus 4 question mark minus 1, 9, 3, 6 minus 2, 2, 4, 8 is minus 1, 9, 0, 4. So let's quickly do some algebra for question mark. Is 1, 9, 0, 4 negative plus 1, 9, 3, 6 plus 2, 2, 4, 8 minus 1, 6, 4, 8. And we're going to divide that by 4 so that the question mark is 158 kilojoules per mole. And so what does that show us? Yes, it does have a leak. Yes, student is correct. Small bond enthalpy. Ammonia gas readily condenses to form a liquid when cooled. Name the strongest attractive force between 2 ammonia molecules. So we have NH3. So it is in fact, if you remember, N, F, and O are highly electronegative. So we're going to call it hydrogen bonding. Let's carry on. Draw a diagram to show how 2 ammonia molecules interact with each other in the liquid phase. Include all partial charges and all lone pairs of electrons in your diagram. Right. N, 3 H's. We have 2 H's for each. In fact, I can remove that middle line to avoid confusion. There we go. And we do have 2 lone pairs. And I just want to draw the lone pairs, and with another color perhaps we can draw the intermolecular forces with a dashed line. Ammonia reacts with boron trichloride to form a molecule with the following structure. State how the bond between ammonia, it's dative, covalent bond. Lone pair donated to boron chloride to form dative covalent bond. Let's carry on swiftly. The following table shows the electronegativity values of some elements. Give the meaning of the term electronegativity. Easy. The ability of an atom to hold a shared pair of electrons closer to it, perhaps. We're going to check this sometime. Suggest the formula of an ionic compound that is formed by the chemical combination of two different elements from the table. The table above. Okay. Let's say an ionic compound. So here is a metal, and boron. Let's not touch boron. CO. Well, we can do lithium dioxide. Let's do that. Lithium dioxide. Lithium dioxide. Or lithium fluoride. Okay. Suggest the formula of the compound that has the least polar bond and is formed by chemical combination of two of the elements from the table. Least polar. So O and F are quite electronegative, so let's ignore those for a second. Perhaps boron and hydrogen? Boron and hydrogen. Boron. No, not really. Oh. I'm not exactly sure. Let's just do CH. H4. That's quite nonpolar. Iodine and graphite are both solids. Iodine, simple molecular structure. Graphite, giant macromolecule. Describe the structure of and bonding in graphite and explain why the melting point of graphite is very high. So bonding, every carbon is bonded to 3 others, forms hexagonal rings, forms layers as well. Carbon still has one electron, which is delocalized and can move throughout the structure so we don't really need this. However, forms giant macromolecule with many strong covalent bonds, require lots of energy to break. Hence high melting point. I just want to add a little bit about the structure. So each has extra electron, which is delocalized. With link in between, hence can slide over each other. I'm not sure how much else I need to write. allows to conduct heat and electricity well. A long layer. Okay, let's carry on. Explain why iodine vaporizes when heated gently. Weak IMF van der Waals because simple molecular structure, small molecule. State why iodine is a very poor conductor of electricity. No charge. No charge. That's clear. Charge. The following figure shows the Maxwell-Boltzmann distribution of molecular energies in the sample of gas at temperature T. One of the axes is labeled number of molecules, which of the following, A, B, or C, describes what the value Y represents in the figure? Most probable energy. That is the energy, the most probable energy X. C. On the figure above, draw a distribution of molecular energies in the sample of gas at a higher temperature. We're going to make it flatter. It's relatively same area. Excellent. The pressure of the original sample of gas is doubled at temperature T. State the effect, if any, of this change on the value of Y. No effect, I think. This question is about Group 7 chemistry. State the initial oxidation state and the final oxidation state of sulfur in stage 1. Okay, in SO2. So this is 2 minus, but since there are 2 of them, it's minus 4. So must be 4 plus. In H2SO4, we have 2 plus here. And we have 8 minus here, 8 minus, so 6 plus. In stage 2, in terms of electrons, well, it gained electrons, and since gain, it's reduction. So reduction, hold on, let's say it gained electrons. And then the second point is reduction, in case. Alright, let's use the half equation for the formation of iodine from iodide ions. Well, we have 8I minus here, then becomes 4I2, but it must have given away 8 electrons, I think. Yeah, so now I have 8 minus 8. Okay. That's it. Thank you for watching. I'm going to self-assess now. Let's go. In fact, let me write my name. And 12, 14, 4, 21. So that's our physical chemistry mock. I'm just going to open the mark scheme in Edge here. Okay, so marking, here we go. So this should open up and tell us what to do. So just like zoom in quite a lot. There we go. Lig turns into G plus electron. So that's one mark. I'd like to use a very strong color. Here we go, pink. So one mark here. Increased nuclear charge. Similar shielding. Oopsies. I don't know what happened there. Okay, so that's 3 marks there. Lower ionization energy, paired electrons, and so repel. Excellent, 3 marks. It has one more energy level, more shielding, and so more shielding. Here's that mark, so 1 mark. Group 2, arsenic. Excellent. Arsenic is poisonous, I think. Fingers crossed. Yes. Excellent. 1 mark here. And then here, I doubt this is right. Yeah, I thought so. Okay, so let's try and solve for 130 centimeters cubed. Now, it says here the total volume of gas remaining. In fact, let me just erase my working here, just because I think it's quite wrong. But anyways, 20 centimeters cubed of ethane was burned. C2H6. In fact, let me write in purple. The volume is 1 more, so 0.2 decimeters cubed. Sorry, let's keep it centimeters cubed. 20. And well, 3.5 volume is 100 centimeters cubed of oxygen. Now we know that the molar distribution is 1 to 3.5. So what does that have to do with anything, you might ask? No, the concentration. Well, I'd like to screenshot this and share this to my teacher. Sorry, just one moment. And while we are doing this question, sorry, just one moment. Alright, so let's just carry on, but I know that that 1 mark is gone, unfortunately. So let's carry on. It's question 4D. Yes, it is. Excellent. Uh-oh, question 5A, we didn't get around to doing it. 2, 5, 4, 2. This is wrong. 2, 5, 4, 2. Question 5B. No question 5B. Why is that? I think there's an issue with this question as well. Oh, goodness. Alright, let's carry on. Explain why CF4 has a bond angle of 109.5 for bonding pairs. Okay. These repel equally. Okay, I think I'd give myself those marks here. But the main pointers is that for shared pair electrons and repel equally as far as possible. Excellent. So this I doubt. Of course it's negative 85. Why wouldn't it be? Not sure about this. Scores just 1 mark for this. X is 2889. Wait, let's do this one again, shall we? I want to try and see how they know how to deal with the signs. At least we got the right number. The idea is there, I guess. But let's do it together. So, C2H6, let's scroll up to the bond values also. So F2, so breaking, we have, well, C2H6, and we don't exactly have N0. Making, we have 2 of this, and we have 6 of this. So let's just find out their values. 2 times negative 680 is negative 1260. 2 times negative 269 is negative 538. So making, we will use these values as they are, but breaking, we need to subtract them. So negative question mark, minus 1260, minus 538 is minus 2889. No, that can't possibly be right. Ugh. Why is this the case? I don't understand. 2 times negative this plus this minus x. Yeah. So 288.9 minus 1614. Where did 1614 come from? There's the fatal error. 1614 here. And so let's try that again. One 614. Answer negative 889 plus 1260 plus 1614. Okay, so negative question mark is 85, and so question mark is negative 85. So I guess we understand that one in a sense. Let's carry on. This one definitely we got wrong. Definitely. Oh, we got it right somehow. So 3 marks. Why? Because we didn't compare it. So because bond enthalpy is less than CH, for example, or CF, or HF. So, okay. Question 7. Hydrogen bonding. Excellent. So this one I was a little bit confused by. Lone pair, correct partial charges for the H bond from lone pair. Okay. So we got 2 out of 3 for this one. Sorry. Wait, hold on. Why is this out of 3 here? I think there must be a mistake. But anyways, I'd just like to draw the correct diagram here. So N, we have 3 H's, and these are partially positive. And this is partially negative. And we do have a electron cloud here. Sorry, lone pair here, and this is going to be attracted to the positively charged, well, partially positive. And with another electron cloud. So I in fact want to write this partial charges for ammonia. Okay, next, dated covalent bond. Lone pair donated to BCl3. Excellent. So we got that bond. That mark. Sorry. The power of an atom to withdraw toward itself. I think we got that one, but just for good measure, the ability of an atom to attract a shared pair of electrons more closely to itself. Excellent. in a covalent bond. Electronegativity, sorry, I'm just writing this on my notebook, is the ability of an atom to attract a shared pair of electrons more closely to it in covalent bond. So that's quite important. In fact, I will highlight it. Just one moment. Alright, so let us carry on. Okay, since I wrote or, we can ignore this. However, it was a silly error on my part. It was in fact 2 lithium oxide, but I did get to mark for that one. And BH3, let's take a look at BH3. BH3, that was my fault. Okay, iodine is molecular, excellent, and graphite is giant or macromolecular, excellent. Every carbon is bonded, we have layers here, connected by covalent bonds within each layer. Oh, I forgot to mention covalent bonds. Van der Waals between layers, excellent, and many, excellent. So we just forgot that covalent bond here, so I would give it a 3 out of 4. Weak van der Waals. Okay. No charge. Does not have what did it say here? Delocalized for free electrons. Okay, might I just add this here? Iodine for electricity does not have delocalized electrons, so I just wanted to add that here. Let's carry on. Question 9. Well, number of molecules. Look at that one. Alright. C, yes. Excellent. So we got that mark as well. No effect. Excellent. That's 4 plus 6. Excellent. Gained electron. Ooh, this one was a little bit tricky. I thought that. Alright, so now we just have to tally up the marks. So 1, 2, 4, 5, 6, 7, 8, 8, 9, 10, 13, 15, 16, 18, 19, 20, 21, 22, 24, 25, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 39. 39 plus 11 is 50. 39 divided by 50 times 100 is 78%. So obviously we need lots more practice on this, mostly related to definitions and that kind of thing, so bye.